Okay, so part B. The next thing we got to do is C. Derive an equation for the distance the object travels. And let's actually put this on a different page so that it's easier for us to look at. Now, the nice thing is we put in a whole lot of work in part B to derive that velocity function. And if we go back and take a look at that function, yeah, it looks gross, but it's an exponential function. And the nice thing about exponential functions is the integral. Well, actually, let me not start there. The derivative of exponential functions is itself. It's an exponential function. So that means that the integral of the exponential function is probably going to be itself. I mean, there's going to be some friends there, most likely, but who cares? Okay, great. So let's rewrite this function real fast on the next page. That was v of t was what? V naught e to the negative k over mt, right? That was our velocity function. So remember that v is what? Velocity. Yes, but at the same time, have what? Lead? What kind? 0.5? Oh no, I have 0.5. What is velocity? What relationship does it have with it is dx dt? So I can replace this with dx dt is v naught e to the negative k over mt. And then I can separate this thing if I wanted to. This is c. Yeah, it's hard to see. Haha. I can split this variable up. Now, I don't need to actually do much of separation of variables. The right-hand side doesn't have any x's in it, so I don't have to bring anything to the left-hand side. All I got to do is bring dt over to the right-hand side. So that's exactly what I'm going to do. If you don't like what this looks like and you're not really comfortable with integrating this thing, you could do a u sub if it makes you feel a little bit better. You could say that, yeah, I guess you could say u is negative k over mt. Actually, I don't really need the negative, but whatever. And then du is negative k over m dt, and then replace that in this equation. You don't really have to, but...
Wait, so is it saying that, is the first equation saying that the terminal velocity is going to be 0?
Yes. I mean, that would make sense because this thing will eventually stop. There is no force. If we look back at the picture that we had originally, there is no force that pushes this thing to the right. There isn't. There's just that friction force that's stopping this thing to the left. Ultimately, this thing is going to stop. Period. That's it. So yeah, that's a good thing to do. Double check. Take a look at that function. Eventually, if I plug in a big enough t, e to this is going to go to 0. Multiply that by v naught, 0. Yeah, you're right. Okay, so do I have to work out this whole integral, or can we just kind of skip through this and get what x is going to be? Who wants to tell me what x is going to be? Do the integral. David, do the integral on your paper and tell me what I'm going to get.
Of what?
Oh, actually, then I'm going to have to replace this. Sorry, let me rewrite this a little bit.
Oh, it's going to be, wait, is the velocity, is it using velocity?
There we go. V naught is a constant, yeah.
Okay.
Also, I can't, like, it wouldn't make any sense to move it to the other side because that's dx, right? So it's not going to integrate with V naught anyways, so. And it's not going to integrate with dt.
Is T negative mass velocity over K times the negative K.
So the integral of e to the u is e to the u. All right.
Okay, so dx. Why do you only integrate? Oh, because the rest is constant. Okay, sure.
Yeah.
Wait, you have to also integrate the other side.
I do,
So
right? I should also technically put in my limits of integration, right?
Yeah. I mean, that's it.
From some initial position to some final position, from my time t equals 0 to my time t final, right? Okay, so this is going to end up giving me x final minus x initial equals negative m v naught over k e to the negative k over m t.
Well, how would you do that? No.
Well, the integral of e to the u is e to the u, right?
Okay.
So then I'm just going to plug back in what u was. U was negative k over m.
Then you still have limits of integration. You still have to evaluate between.
But t initial was 0.
Sure. Oh. Okay.
E to the 0.
Well, that'll give me 1. Yeah, he's right. Okay, he's right. So let's...
Is that plus MV not
Let's make this a little bit cleaner and move it up farther over.
Aren't you normally supposed to do u evaluated by k? Yeah, like at least the way Fermat taught us, when you do u sub, you have to change limits of integration.
It really depends on how you want to do it.
That's the way.
No, there's a lot of people that do it that
I
way.
don't like it. It's very tough.
It's not. It really isn't. You
Because
can.
You really show your work. Like it's. Yeah.
Dude, I've taken calculus professors with PhDs that do it that way. Because honestly, like the nice thing about U subs is sometimes they make your functions much, much nicer to deal with. They really do, right? But usually, especially in this case, like why would I bother? Like why am I going to bother? It's not going to make my life easier. Additionally, I'm not going to leave my function in terms of U. Why would I have a kinematic equation in terms of U?
Wait, so if you
I want my function in terms of T.
You only taught us how to do it this way. I know there is another way, but we only learned this way.
Oh,
Yeah.
go back.
Yeah.
What?
Substitute backwards. Unsubstitute, if you will.
Like
Right?
once you integrate, instead of integrating with u, replace u with
What it was before.
And then
No, after you integrate. So, okay, let's take it step by step then. Let's take it step by step. Okay. So what is the integral of dx? X. Okay, so x evaluated between x initial and x final. Okay, that's this side. Equals. On that side, I'm going to get negative m v naught over k. And then what's the integral of e to the u? E to the u. Now, evaluated between some stuff, but I'm not going to bother about the evaluation just yet, right? I'm not going to bother about it, because what I'm going to do, instead of doing e to the u, I don't want to, because I don't want my function in terms of u's. I don't want any of that stuff. Forget it. And honestly, it won't be in terms of u, but I don't want to do more work than I have to. I really don't. What was u? Negative k over mt. Okay, so negative k over mt. There we go. Instead of u, I'm just going to write negative k over mt. Bam, that's it. That's what you meant. Okay, now, evaluated from, what were my original bounds before I even made a substitution? Okay, from 0 to time final. Now I don't have to do anything. Now I don't have to like find new limits of integration.
Yeah.
Okay.
It's not much that much.
It isn't. It isn't, right? But if I've got 3 minutes left on this AP exam, why am I going to waste my time? Even if I had 30 minutes left on this AP exam, like, this is a step, that's usually a step that I never do.
The two are identical.
Oh, 100%, yeah, 100% they're identical. But, like, why would I care? Honestly, like, why would I care?
Leave it in terms of, oh, okay, so you're saving a little bit of time the fact that it's zero. That's the only thing.
No, and also
And
you
then I
have to
don't.
say when t is 0, u is blah.
Yeah, when t is 0, what does u become? Who cares? I don't care. I don't want a function of u. I want a function of g. Okay, so now let's figure this guy out. So this will end up giving me x final minus x initial. That's technically delta x, I guess. Whatever. I don't really care. Does it want me? No, it wants an equation of x as a function of time. So it really wants x final, right? X of t. That's what it really wants. Okay, equals. I'm going to factor this guy out here in the on the right-hand side. I'm going to factor out negative m v naught over k. So negative m v naught over k is going to come out. And then I'm going to have e to the negative k over mt. And then if I plug in that, I'm going to get minus 1. Now, it's easier for you guys than for me. Go back to the beginning of the problem. At time t equals 0, what does it tell us about its initial position? Does it say that its initial position is also 0? Beautiful. So then I can erase that and have this function. X final, or x of t, if you will, is this garbageness. Okay, that's not too bad. A couple of things to note. In this form, it might not. Yeah, x final. Well, this is t. Some function of t. After.
This is a function of t?
Yeah.
How do you get that?
If you want to say t final, like t final is some value of time after. What value of time do you want? Pick one. Pick a time.
Oh, alright, so you took an integral of a
Of a very flexible time. Yeah, very flexible time. I explicitly did not define it for a reason. Yeah, I didn't define it for a reason. Right? This might not be super obvious very quickly. What this thing actually, it's a shift. Yeah. Which way? I think it's a shift down, actually.
Oh.
Right? Because this isn't affecting.
When it's outside it's down?
Well, if I distribute this guy inside, if I distribute this in, it's going to be e to the t.
Oh, yeah, you're right.
Actually, no, never mind. It's a shift up because there's a negative here. Sorry, my bad. There's a negative here. So this is going to be e to the t shifted up a little bit. Okay. So now it's asking us to graph it. Anybody want to come up and try to graph it? Nobody wants to come up and try to graph it?
This is very
I
scary.
could try.
Come on, Gabby, come and try it. You can do it. You want to do it in green?
Maybe all three are
Is this less than 1 or more than 1? What was the initial? Do we know?
Actually, there's one thing I don't like here. Because if I take the derivative of this, the signage cancels out. That negative needs to go away.
Why would you take the derivative?
If I take the derivative of this to find v...
yeah, it's good. Because v is positive.
Oh, yeah, right, positive. Yeah, never mind. Yeah, you're right, correct.
Wait, is this more than 1 or less than 1?
That's a great question.
What's
Well, v initial is a positive number.
V
Okay.
initial is...
M is a positive number, and k is a positive number.
They never gave us v initial.
They never gave us any of these numbers.
Yeah.
So they're just asking us to sketch
They
this
either
function.
Stretched or
I think they just want us to have an idea. They didn't give us any axes values, so it's not like we're getting actual value. I think they're looking for trends.
We know it's moving to the right, so it's positive.
Yeah, we know that the distances are positive.
Okay, and since it's negative, does that mean it's what?
Well,
Yeah,
it's
we see
moving.
that location is negative. whole thing evaluates to negative.
Okay,
because
hold on.
it's
This right here
Yeah.
is negative e to the right.
That right there.
Yeah, that's right. Like it's shifted downward.
Since it's
below the
shifted
x.
downward,
Yeah.
what you're doing. Wait, no, it's shifted up.
Down.
Well, the negative,
Oh,
and then a negative.
negative.
Yeah, well,
Yeah, it's just gonna be like. And then you're gonna have.
some value. It isn't, yeah, you could just some value, some asymptotic value. Okay.
Is there one or no? Alright.
Well, no, because it's that multiplier right there. Okay. Is there another part? D. Determine the distance the object travels from time t equals 0 to time t equals infinity. Well, and then once we do this, we can take a look at the solutions. Big, ginormous hint from time t equals 0 to time t equals infinity.
When it's infinity, e to the whatever is going to be 0.
Yeah,
So you're
they want us to take the trends.
So you're going to
Oh, that looks like an A. X to the Avengers equals, what was that function again? Negative mv naught over k e to the negative k over mt minus 1. Okay, so here's our function. Yeah. Okay, so if I go to, what were we saying, Gabby?
Oh, I did it wrong.
Don't look ahead, man. So if I plug in infinity for time, what happens to this? It shrinks. It goes to 0. So this whole thing goes to 0. It starts to approach 0. So that means that my distance gets closer and closer and closer to this value. So the limit as time approaches infinity of x of t is mv naught over k.
I did it wrong because I failed to consider the isolation wasn't negative, which means that it's not going down.
Oh, hold on, wait. We're not there yet. Wait. Give me a second. Okay, so are we cool with this?
Yeah.
Okay, let's go back all the way to the beginning, and we'll look at the solutions from part. Oh, wrong problem. From part A. Okay, so the solutions are right here. All right, so part A has 4 points that you can get. For an expression of Newton's laws, F equals ma, you get 1 point. We got that.
Would you have to explicitly write F equals ma, or can you write like net F equals forces minus forces equals ma?
That means the same thing.
It does.
Yeah. And then saying that your net F equals negative kV, you get a point.
It does not do that.
And we did that. So we got that point.
Wait, so in mine I wrote negative kV equals ma, which if on the line before that I wrote the net F was that. So can that be assumed?
I think those are your 2 points, right?
Can that be assumed for that?
No. Okay, hold on. For 1 point, you said F net equals ma. Well, F net equals some stuff equals ma, right?
Yeah.
That's what you said?
Yeah.
That, I think, is 1
That I
point.
got, sure. But the second point where it says you have to write F net equals negative kV, I didn't write that. Instead I wrote negative kV equals ma. And on the line above that it said F net equals ma, which means that I already defined that as meaning.
That's actually a really good point. I'm not 100% sure. I would give it to you because I think that's reasonable. I would give it to you. I'm not 100% sure if they would, but I think a reasonable person would. For calculating the correct acceleration corresponding to the initial velocity, so you're literally setting them equal to ma initial and k v naught, which is what we did here, you get a point. Let's take a look at those signs really quickly. Notice they didn't put that negative in the A, right? And the reason why they didn't do that is so that the signage of the force will help tell them what the signage of the acceleration is. They didn't put it in there, so they didn't assume which way the acceleration is. The force will tell them which way the acceleration is. For the correct direction, indicated by a negative sign or the words to the left, they got a point. So we would have done really well. Part B, 6 points. So that calculus stuff will really give us a lot of the points in this question. So that's going to be this next page. 6 points. Let's see, 1.4, recognition that A is dv dt. That might not fly. It might fly. I didn't explicitly say A is dv dt.
It's the same thing as our previous situation. You said A equals that and dv
Okay,
dt equals
so this might be one of those situations where the grader might be lenient. I'm trying actually this summer to go be a grader, so I'll have more first-hand experience, hopefully. Okay, 1 point for saying dv dt equals negative kv over m. Important here to note is that they don't have kv naught, because it's not v naught anymore. Now it's that function of v. So
V of t.
that's what, it should be v of t, but whatever. We've got that here.
So at some point it dropped v of t and started using v after v0, but not as a function. And v0 is a constant value. Is it correct? Like, because I thought that would be the
because you're integrating from the initial, or time initial and time final,
those
and
are very different values, they're not functions of time. Because you can't have
because
V0.
you're picking 2 points in the velocity
you can't have
function.
V0 as a function of time. V0 will always be the same as V0.
Yeah.
But
Okay.
the problem is, eventually, at the end, we ended up using Vf and Vt and just slopping on it as a function of time in the very end of the integral.
Yeah.
And that looks terrible, and I look where I messed up. Like, where should have I started writing as a function of time?
To be honest, I don't think I have a satisfying answer. I don't think I have a very satisfying
Okay,
answer.
why don't we just
It might be like a good idea to ask like a more mathematical physicist, like someone with a really strong
Are they
math.
more of a stickler for the notation stuff?
Probably. Well, it depends. It really depends. A lot of physicists aren't very big sticklers for math, like notation. Mathematicians are more sticklers. But okay, so far we just get that 1 point for dv dt and 1 point for the separation of variables. That's really it. Note that you don't need to bring the k over m with the v. You really just want that v by itself. You want to try to separate and make your life easy.
So you could if you want.
Yeah, you can. You can, but I guess. All right, so for integration, wow. You really just get 1 point for the integration. The reason I think is because it's a pretty easy integral. It's not like, remember that other drag problem that we had that had 2 terms, right? It had the gravity force and the velocity-dependent resistant force. This one's much more straightforward. So 1 point for the integration. The graph is going to give us 3 points. 1 point for showing us that the velocity is the initial velocity at time t equals 0. Did we show that? We did. Okay. 1 point for a curve that is reasonably representative of an exponential decrease. So it's got to be somewhat curvy. I don't know what else is reasonably representative. I would actually put the third point as part of the second point, because reasonably representative of exponential decrease actually also, to me, means that it should approach 0 as time goes to infinity, because that's a very key characteristic of an exponential function.
Not necessarily 0 with some aspect.
Okay, yeah, very true. A non-shifted exponential function.
We did approach the number, but we screwed up the f.
For the other function, for
Was it the other one?
position, not for velocity. This one's position.
Oh, so we got the-
I'm sorry, this one's velocity. The other one was position.
Oh, okay, that makes sense. 0.
Yeah.
Makes perfect.
Okay. For part C, this one was position. 1 point for saying that v is dx dt and then writing the function. Okay.
We didn't do that.
Well, we said, again, we did that same transitive property thing. We really got to stop doing that. We really got to start saying it explicitly. More and more, I'm saying be explicit. More and more. I know for sure in AP Physics 1, 2 years ago, I went to a workshop where in one of the problems, it was a very simple problem. It was a free fall projectile motion problem where they had two balls, same mass, same everything, same height, same everything, except one of them was dropped and the other one was horizontally projected. That's it. That's the only difference. And then they asked if they landed at the same time, and if they did, why did they land at the same time? And they were looking for 4 major things explicitly, and then they gave you a 5th point for something. So I'll tell you the point distribution. So the 4 major things they were looking for was a statement about how the x and y axes are independent. They don't influence each other. A statement about how both of them had the same height. They started from the same initial position. A statement about how both of them had the exact same acceleration. You have to say all of these things explicitly.
They don't have the same
And-
acceleration, they have the same acceleration in the y.
No, they also have the same acceleration in the x too, 0.
Well, assuming there isn't a jetpack.
Yeah, but it was horizontally projected. It wasn't like,
Okay, yeah.
wasn't
Yeah,
dynamics.
But
But
it was just
it was just
arbitrary.
like flicked or whatever, And the important part there is they wanted you to say that they had the same acceleration. So if you said something like, they both feel gravity. Okay? What does that mean? You don't necessarily get that point. What is it? Okay. Why is that important? Why? Because they don't want you to just stumble into points. They want you to prove that you know what that means. That wasn't the part that got... I was in a very small group, workshop. It was only maybe about 12 physics teachers. There was one physics teacher. She was a Russian lady. She was maybe like 31. She was very young. She got very upset. That wasn't the part that upset her. The 4th one was the part that upset her. You had to explicitly state that both balls started with an initial velocity of 0. You had to explicitly state that they started with an initial velocity of 0. But in the y they had an initial velocity of 0. But the problem said that they were released from, one of them was released from rest. And it was explicitly said. So the teacher said, why would the student have to say that it started with a velocity of 0 if the problem told them that it was released from rest? And the lady said, well, College Board wants to know if the student knows what rest means. And she goes, everybody knows what rest means.
Yeah.
Like, that's stupid. Why would you withhold a point for that? No, College Board wants to know. Blah. She got very upset. It was 15 minutes of yelling, legitimate yelling. I actually wanted to take my phone out and record this. I was texting somebody at the time, and I'm like, this is insane. This is like Jersey Shore. It was amazing. It was amazing. But this is an example I give every year because College Board is really, especially for AP Physics 1, and from the workshop I went to this year, they're trying to make AP Physics C more rigorous like AP Physics 1. Not exactly like topic-wise the same thing, but they're trying to get to that level because, and I kind of agree with this, when somebody can just luck their way into getting an answer.
Actually, like ridiculous.
Oh, that level of it is ridiculous. I agree. That level of it is ridiculous. But the spirit of that, I agree with.
When you did luck into it, you do it perfectly, just incorrectly write it in there.
So there needs to be, when you set rules in stone like that, there's a problem. So there needs to be flexibility. I agree with that, right? That's why they only take in physics teachers to read them and to grade them. I get that. I understand that. But that's where they're going with it. They're expecting, to get a certain standard. That's the thing. All right. Here's the integration, and here is our answer. Now, it looks a little tiny bit different than ours because they distributed that negative that they had in the beginning. We did not. So you'll notice they have 1 minus e to the whatever. We have e to the whatever minus 1. And the reason is because we have this floating negative in the beginning. If we were to distribute that negative, we'd get the exact same answer they did. It does not matter. It's equivalent, 100% equivalent. So there is our equation. These points were awarded if a correct integration was performed using an incorrect expression for u. That's just 1 point. These points were awarded if a correct integration was performed using... Oh, I don't know why they didn't want... Okay. So our graph should look like this. With
written on like a typewriter or something, or just a weird font?
no, probably a typewriter. I mean, this is a question from 1996. Yeah, I mean, an electronic typewriter, most likely,
What's that?
right? Like a special type of typewriter. It's a more advanced typewriter, but yeah, still. For a reasonable concave down curve, where it starts at x equals 0, at time t equals 0, and it approaches an asymptote as t approaches infinity. And those two things are really important, because if we take a look at our function, yeah, it does approach an asymptote. Okay, that's not bad. But I did ask you when we got our function, I said, where is it at x equals 0? Where is its initial position? And you did tell me it started at 0. Right? When we wrote our function, you did tell me it started at 0. You told me that, right? So it can't start all the way up there. It has to start at the bottom. That's number one. That's number one.
Also, if you look at the acceleration, it's negative.
The acceleration function is negative, which means my function should be concave down. The other way to think about it, if you don't want to, that's a calculus thing, which is really important. If you don't want to think about it, it's slowing down,
That's true.
right? It's slowing down. That's another thing. Okay, we've got 10 minutes. There's another question. These are the two questions that I gave you guys on Monday, I think. Yeah? Have you guys had a chance to take a look at these?
These two?
Yeah. No? The first one is a forces question. It's a friction question with circular motion.
Do we try it out first?
Yeah, that's fine. I don't mind doing that. I can no longer pause that, so I'm just going to end it.